Good afternoon, everyone, and thank you for joining these sessions. My name is Gabul Kurniawan from Universitas Gadjah Mada, Indonesia, and today I'll be presenting our work titled AgCyRAG, an Agentic Knowledge Graph-based RAG framework for automated security analysis. This is joint work with Raihan Firdaus Ardian, Elmar Kisling, and Andreas Hickelhardt. So, cybersecurity analysis today involves massive amounts of heterogeneous data. As you see on the right side, we have system log data. We also have ICT assets informations that contain information about assets. We also have CTI or cyber threat intelligence. So analysts must interpret this source quickly and accurately to detect attacks. While large language models make data interactions easier, they still suffer from hallucinations and a lack of factual grounding. RAG or retrieval augmented generations can help, but standard RAG pipeline mainly work on unstructured text, not structured cybersecurity knowledge graph. Our goal is to combine retrieval augmented generations and knowledge graph within an agentic framework, enabling reliable, explainable, and context-aware cybersecurity analysis. There is a clear gap between text-based and graph-based reasoning. Retrieval augmented generation is good at handling documents, but it somehow lacks understanding of the relationship between entities, like how an attack technique relates to threat actor or mitigations. Meanwhile, knowledge graph offers structured reasoning, but require complex queries like Sparkle, which most analysts can't easily write. So our research question was, how can we build an intelligent system that combines structured reasoning from knowledge graph with natural language capabilities of LLMs? We address this through a hybrid agentic RAG framework. Our main contributions are an agentic framework that integrates multiple retrieval methods, such as Cipher, Sparkle, and vector search, integrations of both structured logs and cyber threat intelligence into the RAG process, a factual grounding using MITRE, entity, and CK, and cybersecurity knowledge base, validation using 3 real-world cybersecurity use cases, and finally, we have made the entire system open source on GitHub. So we call our system AgCyRAG, which is sort of agentic cybersecurity retrieval augmented generation RAG. It combines agent-based reasoning, knowledge graphs, and also RAG pipelines. The architecture enables multi-agent occultations, where different agents collaborate. This is similar to how human analysts define and verify tasks. It merges vector-based semantic retrieval with structured graph reasoning to perform multi-step analysis. Let's take a look at the framework architecture. So AgCyRAG includes 5 specialized agents. The first is the guardrail agents, which filters and routes queries safely. The vector agents, which perform semantic search using embeddings. The Cipher agents for structural log retrieval from Neo4j. The Sparkle agents, which queries external cybersecurity knowledge graph like MITRE, ATT&CK, or cybersecurity knowledge graph. And finally, reflections and synthesis agents, which combine and refine response before producing the final explanations. So together, these agents combine symbolic and sub-symbolic reasoning for comprehensive analysis. And the Sparkle agents we develop use a set of MCP tools that make knowledge graph querying easier. For instance, get all technique, which is list ATT&CK technique. We also have get technique by keywords, with search technique by terms. We also have get technique by tactic, with match technique to attack, and so on. So these predefined functions let analysts access structured data without writing Sparkle manually. This is bridging the gap between analysts and complex graph queries. Let's walk through an example. Suppose an analyst asks, identify suspicious activity by user Daryl and link it to attack pattern. Here what happened step by step. First, the guardrail agents check and sanitizes the query. Second, the vector finds relevant log entries semantically. Third, the Cypher agents extract structure relationship between events. The fourth, the Sparkle agents connect these findings to meta-entity and sequence technique. And then the reflection agents evaluate sufficiency of evidence. And finally, the synthesis agents generate a coherent and factual report. So these pipelines allow multi-layer reasoning from raw log data into actionable thread insight. As for the implementations, this framework is built in Python using LangGraph for agents orchestrations. We also use Neo4j for property graph data and Virtuoso for IDF triples. For semantic retrieval, embedding comes from Hugging Face mini LM model. And our cybersecurity knowledge base, or the Sepsis cybersecurity knowledge base, integrates sources like CVE, CWE, CAPAC, and MITRE ATT&CK. All tools are invoked through MCP or Model Contact Protocol, which allows agents to tool communications. You can explore the open source code at the GitHub as we provide below. Let's talk about the use case. The first use case is about general threat intelligence. In this use case, we test general cybersecurity reasoning. So for example, which MITRE ATT&CK technique are used for privilege escalations. The system queries cybersecurity knowledge graph via Sparkle and returns a relevant technique like privilege escalations or tactic privilege escalation. So this is basically MCP that is executed using Sparkle. And you see the output. This shows that the framework has ability to handle the threat intelligence query and then get the final answer in natural language. As for the use case 2, which is about local log analysis, in the second use case, the local log, system log are asked without using cybersecurity knowledge graph. So for example, if the analyst asks, who is Daryl? What did he do and when? The vector and Cypher agents identify repeated valid login attempts at the specific times, which is a suspicious behavior patterns. And you see in the right side, there are an output from a vector, and we also have an output from Cypher, and those all together are combined, and together we have a final answer, which is a synthesized answer from the LLM, feeding by the data from the vector output and the Cypher output. And for the use case 3, which is a log analysis that involve the cybersecurity knowledge graph context. In this use case, we combine local log data with external knowledge graph. For example, with the same user, Daryl shows failed login. The system links these behaviors to a credential stuffing and password guessing technique in MITRE ATT&CK. It even suggests mitigations such as enabling MFA or strengthening password policies. You see here on the right side, we have all of this output from different agents, from vector output, from Cypher output, from Sparkle output. All together are synthesized in a complete, comprehensive answers generated by the LLM, feeding by the knowledge graph and vector. Right, now let's discuss the key takeaways. So as for the strengths, multi-agents orchestrations closely mirrors human analytical reasoning, and the reflections and evidence grounding reduce hallucinations. The system integrates structured and unstructured knowledge seamlessly. As for the limitations, we still experience that predefined Sparkle or Cypher queries are basically relied. So we are basically limited on this predefined query. And as for the analysis, human oversight remains important for validations because these are LLM, and we need to check whether this output of the LLM gets these hallucinations. For the future work, we want to include autonomous query generations, which is to generate a query autonomously, and we want to have a multi-hop reasoning. To conclude, we introduce AgCyRAG, which is an agentic knowledge graph-based RAG framework for cybersecurity that fusing symbolic and sub-symbolic retrieval through a multi-agents architecture. This enable explainable, grounded, and context-rich threat analysis. In the future, we plan to extend AgCyRAG to vulnerability detections, intrusion analysis, and adversarial robustness testing. Everything is open source at the GitHub. Thank you for your attention. If you would like to learn more or collaborate, please reach out to me at my email, and I'll be happy to discuss potential applications for real-world cybersecurity problems. Thank you very much, and bye.